All right, so looking at the urinary system, this is really applying everything that we've talked about this semester. We're going to be looking at hormones again, revisiting how that affects the renal system and overall homeostasis. So you'll remember from general A&P that the renal system is made up of a pair of kidneys that produce urine. So we have blood coming to the kidneys that needs to be filtered. So think of it as dirty blood coming from the abdominal aorta to be filtered by the kidneys. Remember we talked about the different blood vessels that branch and branch and branch from the renal artery to become the glomerulus. And then whatever is filtered out of the blood enters the ureters. And the ureters take that filtrate, that urine, that the components of blood that are no longer necessary, and sends it to the bladder. And then the bladder stores it until it's ready to be released from the body. So essentially, once it leaves the ureter, it's gone from the circulation. It's not coming back, right? So it's waste. It's done. But what we know is that about 99% of what is filtered by the kidneys is reclaimed back to the blood. So we don't, even though we filter it out, we bring it back by a lot of select processes and hormonal controls. And that's what we're going to really spend a lot of time discussing in this unit on renal physiology. So looking at functions then is removing toxins, waste, excess ions from the blood, putting it into the urine, and by doing that we can shift fluid from the urine or back to the blood. So we can control blood volume, we can control the chemical composition of our blood by the kidneys, and pH, because what ion controls pH? Hydrogen ion. Yeah, if I have a lot of hydrogen ion, that does what to pH? Brings it down, right. High hydrogen concentration, low pH, acid conditions, right? So the kidneys can help control acid base, and we're going to look at that in lab this week. So other functions of the kidneys, they can actually make sugar, make glucose during prolonged fasting. They secrete some hormones, 2 hormones they secrete. One we're going to talk about in this unit, and that's renin. Renin is something that helps control a falling blood pressure, so we'll talk about that. And erythropoietin, remember erythropoietin? EPO is how it's abbreviated. That is something that is secreted when oxygen levels are low. Erythropoietin is secreted, and that increases our red blood cell production. So for people that have really bad lungs, we find that they have a higher hematocrit because of increased EPO production as a result of that chronically low, PO2 from having like emphysema, for example. So that's another hormone that's secreted by the kidneys. And then it also activates vitamin D. We make vitamin D in our skin. Then it goes to the liver. It's changed a little bit by the liver. Then it travels to the kidneys, and the kidneys put it in its final form. So if a person has poor kidney function, what would we expect their vitamin D levels to be? Low, because their job is to activate that vitamin D so we can help it do what? What is the job of vitamin D? Why do we need it? Especially everybody in here, which is of female gender. Mood, yeah, it helps with depression. It actually has a lot of functions, but what's the biggest function that we know of? Vitamin D and calcium go together. Vitamin D is the escort for calcium. Helps you absorb calcium out of your digestive tract so we can get it into our blood and use it to build bone. So we always find that when we're taking a calcium supplement, very often they'll throw some vitamin D in there also to make sure we're absorbing that calcium into our blood. Okay, so the functional and structural unit of the kidney are nephrons. Nephrons are the secreting and absorbing structures of the kidney. So when we say that the kidneys filter the blood, it's the nephrons that really do a lot of that selective movement of ions and wastes across the membranes from urine to blood, back and forth. Okay, so then remember the nephron? It starts with Bowman's capsule, then it's the proximal convoluted tubule, loop of Henle, distal convoluted tubule, all those. So this picture that I have here shows the 2 different types of nephrons that exist in the body. In the kidneys, we have cortical nephrons. Cortical, what's the prefix there referring to? Cortex. So most of the nephron lies in the cortex. So this border here, remember the arcuate vein and artery we talked about in lab. That's here. This is the cortical radiate artery and vein. So most of this nephron lies in the cortex, so that's why it's called a cortical nephron. And what we find is that a majority of our nephrons are cortical nephrons, so most of them, 85%. And then about 15% are these juxtamedullary nephrons. So they have these long loops of Henle with this special vessels, these special vessels called the vasa recta. So I would label this so you remember what that is. That is something you needed to know for lab also. So this long kind of mesh of vessels is the vasa recta. So this is the juxtamedullary nephron, and these are important for making concentrated urine. So if you look at animals that need concentrated urine, which means they don't make a lot of urine, they have to conserve their urine, where would we find animals that have a lot of, which will have a lot more of these juxtamedullary nephrons? Where would we look to find animals that have the ability to concentrate their urine, not make much urine because they want to hold on to a lot of water? In the desert, yeah. Desert animals have lots more juxtamedullary nephrons than we do. We need to drink a lot of water to keep our fluid volumes up. We urinate more than, say, a desert rat does or a snake. Okay, we talked about urine in lab, so I'm not going to go into the physical characteristics of urine again. This is all for lab. Ureters, again, are the passageways for carrying urine from the kidneys to the bladder. So once it leaves, it's done. That fluid is lost once it hits the bladder. I'm not going to talk about that. We're not going to talk about kidney stones. That's all lab stuff. But now we'll talk about the glomerulus. And the glomerulus is a capillary. So it is part of the vascular system. Even though we find it in the kidneys, in the cortex, it's part of the vascular system, part of our blood supply. And what's unique about the glomerulus, it's the only capillary in the body that has an arteriole on both ends. All the other capillaries have an arteriole on one end, and what's on the other end? A venule, but not in the glomerulus. The glomerulus has two arterioles, and these arterioles can constrict, and they have muscular walls. So as a result of that, we see a big pressure difference here in the glomerulus. So this can squeeze and contract and constrict, and so can the efferent arteriole. So that maintains a pressure, a higher pressure inside the glomerulus, because we can slow the flow of substances coming through it by constricting these arterioles. And the glomerulus is specialized for filtration. What does filtration mean? What? Kind of, yeah. We're taking, waste out of the blood, but a lot of it goes back in. 99% of what is filtered from the glomerulus, which means it leaves the blood and enters the kidney, it goes back in to the blood. So filtration isn't as much cleaning as it is just passing something through a membrane. Like when I'm making macaroni and cheese and I'm boiling the noodles and I'm ready to grab the noodles and get rid of the water, you pass it through a colander, don't you? Some of you might, otherwise some people just use a lid to do that. But let's say you put it through a colander. Picture that like the glomerulus. What stays behind? What remains in the glomerulus? What can't fit through those holes of the glomerulus? The bigger things in our blood. What are some bigger things in our blood that we've seen this semester that can't squeeze out of capillaries? Large proteins. Sugar will, because that's dissolved in our blood, right? That's a water soluble. So we should not see large proteins leaving the glomerulus. We should not see, what else? What's floating in our blood? What's the solid stuff in our blood? White blood cells should not be coming out of the glomerulus. Yes?
So like the stuff that's supposed to stay behind is the stuff that we shouldn't see in the urine?
Correct. Yep. So we talked about white blood cells. We mentioned proteins. What else? What else is in our blood? What's the solid stuff in our blood? This is like general A&P question. What? The solid part of our blood? Red blood cells, yeah. We shouldn't see red blood cells coming out of our glomerulus. So there should not be red blood cells, there should not be protein, there should not be white blood cells, there should not be platelets. Any of those solid, larger things should not leave the glomerulus. So if we look at the pressure inside the glomerulus, it's high because the afferent arteriole is smaller in diameter than the efferent, and these have a higher resistance to flow, so that controls the pressure inside that glomerulus. It's like taking a garden hose and squeezing it at 2 points, and the glomerulus is in the middle. Wouldn't that increase the pressure between my two squeezed areas of the garden hose? Yeah, and that's what the efferent arteriole do, is they provide a little higher pressure to make sure we squeeze this stuff out of the glomerulus. But again, we don't want to get rid of everything that gets squeezed out. A lot of it we're going to take right back to the blood. So how we do that, how we get things back to the blood, is the peritubular capillaries. These wrap around the nephrons, and they're right there ready to soak up that stuff that was squeezed out. So filtration is really non-selective. It's whatever is too small to be stuck in the blood is going to squeeze out of the glomerulus, enter Bowman's capsule, and then go into that first part of the nephron, which is do you remember the first part of the nephron, what it's called? Going back up. Yeah, the proximal convoluted tubule. So we squeeze all this stuff out of the glomerulus. It enters Bowman's capsule, and it's headed for the toilet, right? If it continues through the nephron and goes down the collecting duct, after that it's the pelvis of the kidney, the ureter, the bladder, the toilet, or the tree, right? So we don't want that stuff to enter into the collecting duct. We want to put it back in the blood, because if we're squeezing out glucose and sodium, potassium, all these important electrolytes, because those are all water soluble, they can fit through the pores of the glomerulus, we got to get them back. So how they get back is through the peritubular capillaries. So these are very, very tightly adhered to one another through a basement membrane, essentially. Not quite that sticky, but they are very, very close to one another, so substances can leave the nephron and enter a peritubular capillary, and vice versa. It can leave the peritubular capillary and enter the nephron. So this is where the exchange between blood and urine takes place, is here among these blood vessels around the nephron. And where does this peritubular capillary go to? Where does it lead to? If you follow it out of the being looped around the nephron, where does it go to? To a vein, right? To the cortical radiate vein, and then back to the arcuate vein, and then out the renal vein, back to the inferior vena cava, and back to the rest of the blood. So clean blood leaves via the venous system. So dirty blood enters in, needing to be filtered and reabsorbed depending on the needs of the body, and then it comes back via the veins, the venous system. So when we come back next time, we're going to talk in more detail about the glomerulus and how the peritubular capillaries work with the glomerulus to make sure that we're reabsorbing these ions, glucose, and other substances back to the blood.